Hi everyone, welcome to our 5th live stream geometry session. So we're already at number 5 and I don't think we're going to be stopping anytime soon. So if you'd like to join, email me at mgreenb801@gmail.com. So my channel, we recently reached 500 subscribers, which I think is awesome. I just got an email from YouTube. I think it said that all my subscribers would take up, I forgot what they said, like a blimp or something like that. But yeah, maybe in a couple of years it'll be even more. So yeah, thanks everyone for watching my channel. All right, so I'm gonna start with the first problem right now. So let me share my screen. Just a second. I'm trying to look for the right thing to share. Here it is. All right. Can you guys see the first problem? Or wrong?
Yes.
All right. So this is a problem from the Romania team selection test. Romania usually does pretty well at the IMO, so I'm assuming it might be kind of hard, but let's see how we do. Okay, so we have a cyclic quadrilateral ABCD. Let me maximize. Okay. AC and BD meet at X. All right. I is the in-center of XBC. Actually, let me draw it like this. Let me make that point B and that point D. All right. AB and DC meet at J, or they don't meet at J, but I'm gonna denote the intersection point. Just call it E. All right. So I is the in-center of XBC. Okay, I'll rename that I. And X, J is the in-center of EBC. So we'll call those I and J. We want to show IJ bisects arc BC. All right. Let me make this a little bigger. Maybe move it over a little bit. Okay. So I'm gonna draw the center of the circle. Call it O maybe. Let's see. All right. So that's the center of the circle. All right. I and J are in-centers. So if IJ bisects arc BC, that means that OF is perpendicular to BC, right? So yeah, we might want to let IJ meet it at F, and now we want to show OF is perpendicular to BC. That's kind of an idea I have. How do we use the fact that, well, so these are, I and J are the centers of two circles. So I didn't draw the in circles. I think I will. But basically, we have a line joining two centers, so it's perpendicular to their radical axis. I draw the two circles. All right. All right. Okay. Yeah, this is such an interesting problem. It's like cyclic quadrilateral, then you have two end centers that cut the circle at the mid. It's so random, but it's interesting. Not even sure how to begin here. Let me try some things. No, that doesn't do much. If I move things around, it might give me some insight. So, I mean, angles BAC and BDC are both half of arc BC. So basically, we're saying angle BAC is equal to angle BOF, right? So I feel like that has to be useful somehow. Like, what if we extend OF? Like, for example, let's see. Hold on just a second. Yeah, like, for example, if we let OF meet EC at a point G, then we want to show that BODG is cyclic, right? That would solve the problem. Because if BODG is cyclic, then that means angle BOG is equal to angle BDG, which is half of angle BOC. Okay, so I feel like that's progress a little bit.
Can you just repeat again?
Yeah. So basically, angles BAC and BDC, both of those are half of angle BOC, right? Yeah, so angle BAC and, angle BAC and BDC are both half of angle BOC. And so basically, if F were the midpoint of arc BC, then BOF would be half of BOC. And so we want to show that BOF is the same as BDC. And that's the same as showing that BODG is cyclic, if that makes sense. Oh, don't worry about it. Yeah, you're John, or I'm sorry if I pronounce your name wrong, but yeah, it's fine. You can come whenever you want. All right. So how do we show BODG is cyclic? mean, basically we want to show BGCO as like a kite, right? Yeah, I wonder, I'm just going to play around with things. What if I did this? I don't know if that does much. Yeah, I'm not sure how much value there is in doing point G. I'm going to erase it for now. Actually, you know what? I'm going to add it back. Let's see. Take it away. I wonder what the radical axis of these two circles is. Yeah, they can't ever intersect. Let's try something. I'm gonna draw some of the angle bisectors in because we got to start using that somehow, right? Or it looks almost like I think those angle bisectors might be no, I don't think those are actually tangent to the circle. No, because you can see they intersected like that. Um, all right. G and H are the midpoints. Yeah, I wonder, let's see. So if we sort of extend BC, so angle EBC is equal to angle CBG, right? So basically, Angle JBC is half of EBC, which is half of CBA. Let's see.
Yeah, one other thing I found angle BAF I think is equal to angle FTC.
Angle, I'm sorry, what's equal to angle
BAF,
FBC?
since F is the midpoint of that arc, I guess. Yeah.
We're trying to prove F is the midpoint of the arc, so we don't know it yet. If we could prove that
Okay.
it's all right. But yeah, that would solve the problem.
Uh-huh.
Hmm. Yeah, this one is tricky. So, what if I draw like AF and PF? Yeah, but it might be easier to think of the problem the other way, to first let F be the midpoint of the arc and then show I, J, and F are collinear. I think that's a better way of thinking about it, right? That seems like much easier kind of to wrap my head around. So that's what I'm going to do. I'm just going to let F be the midpoint, define F to be the midpoint of arc BC. And then we want to show that I, J, and F are collinear. So if F is the midpoint, like this is kind of interesting actually. There's like a circle. Yeah, basically we want to show F lies on the line connecting the centers of those two circles, right? I wonder what the other point of intersection is. So if IJ meets the circle again at a point, maybe we could find something about that point. I'm just trying something here. I'm gonna check this out. What if I? No, that doesn't really do much. I don't. Let me see if E. No. How do we use the point J?
I could be wrong, but I've seen some of the properties like the figure. If you observe the quadrilateral XBEC, it has two circles in it uh, that is separated by diagonal BC. So there were some properties. I'm not sure I remember it right now, but there were certainly some properties including there. Some formula between the line segments, not particularly in angles, but in line segments, measure of line segments, there were something.
Yeah, now this does look familiar. Like you have like a quadrilateral and two circles, sort of like this. Um, yeah, XBC might not necessarily be a quadrilateral. Yeah, I guess we have to assume that AB isn't parallel to CD for the problem to make sense. Okay, is G the point where the mixed linear incircle of triangle CAD touches CAD? Uh, that's interesting. Sorry. Let me try that. So I'm going to look at what Urijon said, which sounds really interesting. So let me try to draw the mixed linear incircle. Yeah, I don't know a super short way to draw the mixed linear incircle other than this. But I will do it. See, I'm gonna hide a bunch of this stuff later, but yeah, I am trying to draw the mixed linear incircle. Hold on just a second. Is that really it? Yeah. Okay. Let me hide a bunch of stuff. I'll explain to you guys what I'm doing, but I'm trying to use Urijon's suggestion. What did I do? Hide that. I think that should be a good. Oh, let me hide this guy. There we go. Okay, so let's see. Let me make this figure a little better. So G, yeah, no, I don't think G is where the mixed linear, oh, where it touches the circumcircle. I don't think G is the tangency point of mixed linear in a circle. Let me erase some stuff. Undo all that.
I feel like angle IBJ and ICJ are equal.
That sounds interesting. Let's see, I'll just use measure. Because if they are, I think it's likely an angle chase. They are, yep. I'm guessing that should probably be an angle chase, right? Because IBJ is half of EBD and ICJ is half of ECA. And yeah, so they're equal by an angle chase. All right. So that's kind of good information. Because yeah, if they're equal, that means the triangles IBJ and ICJ, their circumcircles are the same size. So basically that means that F lies on the radical axis of those two circles. I kind of like that. Let's see, so if I draw those two circles, IBJ and ICJ, they're the same size, and I want to show that F lies on the radical axis of them. So I want to show that F has the same power with respect to them. So basically, I want to show F is the same distance from their centers. That's kind of interesting. I kind of like it. Let's see. If I can show F as the same distance to the centers of these two circles, that would solve the problem. Let me try something. It almost looks like IGHJ is a, oh yeah. Well, IGJH is a rhombus. I wonder if triangle FHC is congruent to triangle FGB. I think that is true. Let's see. I wonder if I could make this. So I'm just going to let E be way up there. But I think FGB is congruent to FHC. Let's check that out. So angle FGB is 147.9, and angle FHC. Yep. All right, so if we can show that those triangles are congruent, that would solve the problem. We know that BG is equal to CH. We know that BF is equal to CF. I think we're very close here. We need to show angle GBF equals angle HCF. Wonder if that's obvious somehow by an angle chase. think it might be.
Is it always true that G and H lie on the in circle of BCE?
That G and H lie on the in circle of which circle? Of BCE?
Of BCE, yes.
No, they don't lie on it. It maybe it looks close, but no, if I move around the figure, you'll see they don't lie on the in circle. But yeah, I feel like we're really close because I feel like, although I'm not 100% sure, but if we can show angle FBG equals angle FCH, that will solve the problem. Okay, I think I have an idea. All right, so I'm going to start writing this up. Just a sec. Let me move, I'm going to minimize this for now. Let me move the figure to the right, and I will start typing it up. I really like that idea, though, of showing that angle JBX equals angle JCX. That's like the key to the problem, it looks like. Okay, so right. All right. So we have that. And then we can do the same thing with angle JCX. So but then it's not hard to show that JBX has to equal JCX because I'll write this out. That means that angle JBX is equal angle JCX. All right. And now once we know that, that means that triangles JBX and JCX have the same size circumcircle. Or I'll just write it like this. So the circles JBX and JCX have the same radius. You guys see why that's true? Because if angle JBX is equal to angle JCX, then if you drew the two circles, wait a sec, this looks like I drew a circle through JB and I instead of JB and X. Yeah, let me just, oh no, I did want BJ and I. Wait, now I'm confused. Oh, this should be JBI all along. I'm gonna change it. So everywhere you see X, it really should be I, right? So yeah, no, the circles were right. It's just this should be an I instead. But does this make sense? Why the circles JBI and JCI have the same radius? Because when you draw the two circles, you have the segment JI is like a chord of both circles, and the same angle intercepts that chord. So angle JBI intercepts it in one circle, and angle JCI intercepts it in the other circle. But if both those angles are equal, then since the same angle intercepts a chord of the same length, then the circles have to be the same size. Does that make sense?
Yes.
All right. And so once we
sorry, repeat once again.
Sure. So basically, if you look at the circles through JBI and JCI, they both have JI as a chord, right? And if you look at, in one of them, angle JBI intercepts that chord, and in the other circle, JCI intercepts that chord. And so if JBI and JCI are the same, then the circles have to be the same size. I guess you could kind of think of it like, here's one way to think about it, but if you reflected C across JI, it would kind of have to lie on this circle, because like if you reflect C over JI and it's some other point C prime, then angle JC prime I is the same as angle JBI, right? So C prime lies on this circle, in other words. I don't know if that made it more or less.
At the end, JGIH maybe, yeah, JGIH would be a rhombus, I think.
Yeah,
Because
JGIH is a rhombus.
makes sense.
Yeah,
Makes
that's
sense.
true. All right, so I'm going to move on with the rest of the proof. So once we know they have the same radius, one way to show that J, F, and I are collinear is to show that F lies on the radical axis of both circles, right? Which is the same as saying that F has the same power with respect to both circles. So basically, if F, I guess there's a couple ways of thinking about it, but actually, let me write it out this way. This is probably even simpler. So JI is the perpendicular bisector of GH. All right. And then I'm going to show that FG is equal to FH. So I'm going to show that F also lies on the perpendicular bisector of GH. And I'm going to do that by trying to show that triangle BGF is congruent to triangle FHC. So here's sort of the strategy. So, so we know that BG is equal to HC, since both circles have the same radius. And then also BF is equal to CF, and that's because F is defined, we defined F to be the midpoint of arc BC, right? Okay. So if you look at the triangles BGF and CHF, 2 of the 3 pairs of sides are the same. And now we just need to show the angle between those is the same. I just thought about how to do this, but now I forgot again.
Yes, if BF equals to CF, it solves the problem.
Yeah, so I think I kind of remember again. So we have angle FBG is equal to angle FB, maybe FBI minus angle GBI. And that's equal to let me think about this. BC plus angle CBI minus angle GBI. So write this out for now. Okay. Now, how do we get angle GBI? So
It's twice of angle BJI.
yeah, so GBI, it's like we could write that in terms of yeah, GBI is 90 minus BJI, I think, because I'll just write it out like this. I hate it when it does that. I'm just going to copy this into another text box. So GPI is right, and then this is a if you distribute, that would be 90 minus half of BGI, which is 90 minus angle BJI. So I'll just copy this whole thing. Okay, so then how do we get angle BJI? So FBC, it looks, so I'm just gonna write, so we calculated angle FBG, we can calculate angle FCH in a similar way, right? Okay. And then HCI is 90 minus CJI, using the same idea as before. And FCB, I'll just leave like that. Yeah, so basically, I mean, we want to show that these two things are equal right here and right here. So the 90s, so hold on just a second. So yeah, okay, so we want to show that these two expressions are equal. And I think when we combine them, we get that they are. So basically, yeah, I'm just gonna say, so we have angle FBG is equal to angle FCH if and only if it looks like, I think it's really just an angle chase at this point. Okay, so just sort of doing a bunch of algebra on the spot. So those two angles are equal if and only if that's true. And that looks to be true by an angle. So let me just do a little stuff in my head, but I think that's really just an angle chase that shows that this is true.
Yes, BJI plus CJI is
BJC,
angle
right?
BJC. So, and BJC is 90 plus half of angle BEC.
Yeah, so this is 90 plus half of BEC, and then FBC plus FCB plus CBI plus BCI. That's the same as FBI plus FCI. And yeah, I'm sure you could do an angle chase to show that those are equal. Yeah, I see a way to do that. I'm trying to see if there's like a fast way to do it, but really this is just an angle chase. So I'm just gonna say that these are, I'm not gonna write out the whole thing, but I'm just gonna say these are equal by an angle chase. Whoops, sorry about that. And so just so that we don't spend so long on this. So those are equal by an angle chase. And so that means that triangle FBG is congruent to triangle FCH. So that means that FG is equal to FH. And once we know that, that implies that F lies on JI. And that's because we said JI is the perpendicular bisector of GH. So that makes sense to everyone. So if FG is equal to FH, then that means F lies on the perpendicular bisector of GH. And we said JI is the perpendicular bisector of GH, so that solves the problem. Does that make sense to everyone?
Yes.
All right, sounds good. So let's move on to the next problem. I'm pretty happy we got through that. All right, there's another problem from Romania, so it's probably also pretty tricky. So we have two circles, omega 1 and omega 2, centered at O1 and O2. And they meet at A and B. And then we have a line through B. It meets omega 1 at C and omega 2 at B. All right. And then we draw the tangents at C and B. And they meet at a point E. So I'm just going to change things around a little bit so that we can see the intersection. Whoops. Let's see. Maybe I think one circle, I'm just trying to figure out. Yeah, we just have to make these small enough so that you can see the intersection. See. I guess that looks fine, right? So we call E this point. And the line AE meets the circle through A, O1, and O2 at F. We want to show the length of EF is equal to the diameter of this circle. All right, so that's interesting. I'm going to clean up some of the figure. Oh, that's really interesting. Okay, so we want to show EF is the diameter of this circle through A, O1, and O2. Let me check that that's actually true. So if I drew a diameter, let's say, and I try to measure the length of it using GeoGebra, the diameter has length 5.2 and EF has length 5.2. All right. One sec, I'll be right back, guys. All right, I'm back. Let's see. Maybe we could use power of a point somehow. So obviously O1, I mean, obviously we have a lot of isosceles triangles since all the radii are equal. So EF times EA is ED squared. And if we let EF let's see. Oh no, EF times EA isn't ED squared. It's whatever the power of E with respect to this circle. So I'm gonna draw in the center of this circle. I think it's circle E. Yeah. All right. Call it G. So by power of a point, we have ED squared is equal to EO2 squared minus this radius squared. And the same we could do with EC squared.
I have an idea.
Okay.
A is the center of the spiral similarity that takes the segment CO1 to the segment DO1.
Okay. CO1 to DO1 or CO1 to DO2?
DO2, sorry.
Oh, that's all right. You said A is the center of that, right?
Yes, is it?
I'm trying to think because it's like the intersection of the. Well, let's see. I'm not sure. So basically that would mean triangle AO1C is similar to triangle AO2D, right?
Yes.
It could be. Let's see if that's true. 131. Yep. Yeah, it is. So did you were you able to prove that, or by looking at the figure you thought it looked true?
Just by looking at the figure.
Yeah. Okay. That looks like it probably should be an angle chase, right? Because you can write angle CO1A in terms of angle ABC, and you can write angle DO2A in terms of ABD. So I think using an angle chase, we could show that that's true. So I'm just going to assume it's true for now. So we're assuming that triangle AO and C is similar to triangle AO2B. And then later, when I type up all the text, I'm gonna prove it. That's a good observation. So I wonder, what if we drew the circle with diameter EF? Basically, we're saying these two circles are the same size, right? I mean, yeah, that's a much better way to phrase it. So basically, if we let H be the midpoint of EF, we want to show that GF equals FH, right? So that's the same as showing like AGH is 90 degrees, right? No, not really. But we want to show GF. Yeah, we want to show GF is equal to FH. Yeah, how do we use the midpoint? So one interesting thing is that if we think of E as a point circle, I'm just thinking. So IH would be parallel to DF. I'm not sure where that goes. But yeah, I wonder if GH is parallel to O102. I feel like it should. I feel like it might be. Oh no, actually, I don't think it is. Let's see. Yeah, no, that's not true. Yeah, obviously O1A, O2B is a kite. Can you draw the circumcircle of CAD? All right. Ah, passes through E. You must have seen that. Okay, so can we show that CADE is cyclic? Is that must be an angle chase, but is it that easy of an angle chase? Let's see.
Yes, it is angle chase. You have to draw AC and AD, then AB, then you can just prove because they're tangents.
All right. So yeah, due to all the tangents, we can show that that's cyclic. So I'm going to write out all the angles later. And then how does that show EF is the diameter? EF is equal to the diameter. Let's see. So once we know that, we can use power of a point on F. So EF times FA. So basically, that's another way is to say that I think we want to show F, G, and I are collinear, because then I think we could use power of a point, and then we'd have FE times AF is, let's see if that's true. Yeah. If we could show F, G, and I are collinear, that would do it. Okay. So for wood, is it obvious that F, G, and I are collinear? And if that is true, does that solve the problem? I'm just thinking it through. Check the chat. Raffaello says that's an angle chase. So what are you saying? The fact that F, G, and I are collinear is an angle chase? And how would you show that? I'm just trying to think how the angle chase would work. I guess that's angle FAB plus angle IAB, right? How would you do that angle chase? So angle AIF is equal to AO1F. And angle AFI is AO2I. So Raffaello, how would you do an angle chase to show that FI is the diameter. So in other words, angle FAI is 90 degrees. Consider line DO2. Okay. That also passes through I. BO1 then, yeah, I'm finding a lot of different things. Okay. So DO2, we're saying passes through I. Let's see, is that obvious?
If that's true, then CO1 and I also, they are also collinear.
Yeah. Maybe this is some kind of obvious, I think by spiral similarities, this might be true because we said that triangle CONA is similar to triangle DO2A. So if we extend the sides, I think, yeah, okay. So by properties of spiral similarities, CO1 and BO2 meet on the circumcircle of AO1, O2. And then is the same also true? So I can see why CO1 and BO2 meet on this smaller circle, but I don't see immediately why they meet on the bigger circle. But maybe it's the same idea. I think it might be. Yeah. Okay, so what if I hid those two circles for now? And I hid point I. And what if I let O1C meet DO2 at a point J, and then I want to show that both those quadrilaterals are cyclic. So I'm just going to draw in a few more segments here. Is it clear that J is it JO1 AO2 and F, but for now let's see. Yeah, because we can show that those two angles add up to 180. So actually, yeah. So an angle chase will show that OA1 O2J is cyclic. And then I'm guessing another angle chase would show, I think it was JADE. Let's see, cyclic. Yeah, okay. Because we need to show angle JAE is equal to angle JDE.
I wonder if FG and J are collinear.
Yeah, that's what we're trying to show. We're trying to show
Yeah.
yeah, but even once we show that, I'm not 100% sure how we'd finish off the problem. But I'm trying to see what Irajan said. So J, A, D, and E, can we use an angle chase to show Huh. Yeah, is it obvious that J, A, B, and E is cyclic? I'm not seeing how to show that. Um, is it obvious that C10F? Sorry. See you later, Rafaelo. Can we show C10F is 90 degrees? Seeing so many different things here, but yeah, it's just hard to yeah, is it obvious that C10F is 90 degrees or CO1F?
But for that, you have to prove O1F and CE parallel. I don't see a way.
An easy way to do that. Yeah, it looks a little tricky. Although I might have an idea. So let's say we knew that F, G, and J were collinear. Does that solve the problem?
If they are like collinear, then we have to also prove that means JE, JFE and O1CA are similar.
J, F, E, and O1A C.
O1AC and JFE
And JFE.
are similar.
Yeah, I see what you're saying. That would be the same as showing that those are similar. You're John. I still haven't proven that that is it ACED or AJED, but I still haven't figured out how they're cyclic. At least not in my head. Yeah, yeah. I still haven't shown that ACED is cyclic. Oh no, ACED is cyclic. I can do by an angle chase, I think. Yeah, but the fact that that circle passes through J, I haven't proven. But let's see. I think once we show ACED is cyclic, then it's not hard to show J also lies on that. Yeah. Okay. I think. Okay. So let's say we prove that too, because I think that's also an angle chase. Now. Let's see. Can we show that angles? Can we show O1F is parallel to CE? I think that should also be an angle chase. Okay, so I see a way in my head, I'm going to write it all out, but I see a way to prove that Fj is a diameter. And so the question is, how do we finish it off? I feel like we're so close. If I know that Fj is a diameter, can I then show that Fj is equal to EF? See. And I feel like that would also be an angle chase. Yeah, because I could show that I could calculate angle AFJ, and I could calculate angle AEJ, and if I can show AFJ is twice AEJ, that would solve the problem. So yeah, this is a lot. I see a way to do it, and I'm sure this isn't the shortest way, but I'm gonna write this all up. So yeah, there's in the comments or on the Discord channel later or on in the YouTube comments, you guys can post a faster way to do this. But for now, let's see. Okay, yeah. I'm gonna start from scratch, and I'm going to type up a bunch of stuff. Okay, so we start by letting O1C meet O2D at J. And then first I'm going to prove that O1A O2J is cyclic. Whoops. Now, let me move this way to the side just so I can. Okay, that's point J. I'll just keep it in mind. All right. And so that means that JO1AO2 has to be cyclic. I don't know yet. I didn't prove yet that F lies on that circle though. So let me move that for now. Oh, but we know that F also lies on this circle because by definition, so because F is defined to lie on that circle. Okay. So I'll just add F here. And then we can use an angle chase to show that JADE is cyclic. Okay. So, whoops, sorry.
Does O1A, O2F look like a isosceles trapezium to you?
O1A, O2F? I don't think so. I think, whoops, sorry. Yeah, I could just check that quickly, but so I had an idea to, let's see. O1A is 1.2, O1F is 0.9. So yeah, that's not necessarily an isosceles trapezoid. But I had an idea in mind to show that JADE is cyclic. I'm just trying to remember. So I think I may have hidden more than I should have. So let me unhide, yeah, this segment through C and E, I should draw. Okay, so basically, because that's part of the problem. So angle ECO1 it has to be 90 degrees, right? So angle ECJ is 90 degrees and angle EDJ is 90 degrees for the same reason. So yeah, JCDE is obviously cyclic. All right, so JCDE is cyclic. But we have to show it passes through A also. So JCDE is cyclic, and can we show JCAD is cyclic? I think that's just an angle chase. So yeah. Yeah, I feel like this problem shouldn't have taken, it's just, yeah, thinking about how to write up the angle chase. I don't want to leave it out of the video, but yeah, so since ADO2 is equal to, this should be CaO1. So JCAD is cyclic. All right, so that means that all 5 of those points lie in a circle. So I'm just going to add E in. Okay. So JCADE is cyclic. Now I'm going to draw in the center of this circle. Let's see what it was named. That's circle C1. Okay. Whoops. Didn't want to do that. It's the center of E. Okay. There we go. Whoops. Okay, so now we wanted to show that angle JAE is 90 degrees, but that's clear, right? Because okay, so that means JF is a diameter. All right. And so I'll draw that in. And I'm trying to remember, how did we finish? Oh yeah, we can finish with an angle chase. So angle JFA is equal to at least I thought we could. Let me just think about this quick. JFA is equal to JO2A. And that's equal to angle CaO1. And that's equal to angle oh, actually, I think I see how to do it. So angle, Let's write it like this. Right. So angle JFA, it's equal to angle JO2A, and which is twice angle JVA. That's because this triangle is isosceles, O2AD. So since O2AD is isosceles, JO2A is twice JVA, and JVA is the same as JEA. So if JFA is equal to twice JEA, then that means triangle JFE is isosceles. And so EF is equal to JF is the diameter of omega. So yeah, I mean, once you see the right ideas, this problem isn't hard. It just took us